Hey, this is Mr. Ariel, and I'm here today with another part of the notes for atomic bonding. Today we're going to learn about polar covalent bonds and metallic bonds. Now, normally I don't put any real notes on the first slide, but for today I think it'd be a good idea if you wrote down the three types of bonds that we're going to learn about, and then we'll add some information onto each one, kind of as a summary. You have notes on these two types of bonds already, but they're kind of on separate sheets of paper, and it's helpful to summarize everything in one place. So we know that ionic bonds are between a metal and a non-metal ion, and covalent bonds are formed between two nonmetals. And ionic bonds involve the total gain and loss of valence electrons, but covalent bonds involve them sharing those valence electrons. Now the last kind of bond we're going to learn about today is the metallic bond, and that's a bond between metal atoms. Instead of gaining or losing or sharing electrons between two atoms, this type of bond is thought of as a sea of electrons. I'll show you in the notes later, but it's where millions of electrons are flowing back and forth around millions of metal atoms. In other words, this bond isn't just between two atoms, it's between lots and lots of metal atoms. Now, moving on, we've already learned about covalent bonds in a previous lesson, but there is another level of detail that I need you to learn. There are two types of covalent bonds, and the difference is on how equally shared the electrons are. Non-polar covalent bonds are those kind of bonds where the atoms pull equally on the electrons involved in the bond. Now, in a previous lesson, we looked at O2 and N2, their formulas for oxygen and nitrogen gas. And the structures we drew, oxygen has a double bond and nitrogen has a triple bond, but these electrons are being shared, so it's covalent. Now, electronegativity is an idea we learned about in a previous unit, but we didn't really do anything with it at the time, we just learned about it. So electronegativity is the ability of an atom to attract electrons when the atom is part of a compound. On the periodic table that you have for class, you can see the electronegativity for every element in the box. For oxygen, it's this number right here, 3.5. Now the higher that number is, the stronger that attraction for electrons will be. So with both oxygens having an electronegativity of 3.5, I hope you can see that they're equally pulling on these electrons, and if we were to subtract them, 3.5 minus 3.5, of course that works out to be a 0. And you can see on this table here that that lines up perfectly with less than or equal to 0.3, and so that's a non-polar covalent bond. Go ahead and pause the video right now and get all of this information over here on the left into your notes. But leave some room over on the right. You can tell I'm going to add some information there in a few minutes. Now, if we have two atoms that aren't identical, but their electronegativities are close to each other, let's look at an example like that. Here I have hydrogen and I have chlorine. Hydrogen has 1 valence electron and chlorine has 7. Now, to make this covalent bond, chlorine would let hydrogen borrow that electron once in a while, and then hydrogen would let that single electron go around chlorine, so both end up with a full outer shell. But if you look at the electronegativity values for these, hydrogen is 2.1 and chlorine has a value of 3.0. So if you were to subtract them, 3.0 minus 2.1, that works out to be 0.9. And on my table, that's solidly between 0.3 and 1.7, so it's a polar covalent bond. And so that means the electrons are not shared equally. And they're going to spend more time around chlorine because it has a bigger electronegativity. Now, let me draw out a different picture. I'm going to pull it right down here. And so we're going to draw hydrogen. We're going to draw the shared bond of those two electrons, and I'm going to put those same unshared electrons back around chlorine. Now, what I'm saying here is those electrons are not shared equally, and they're going towards the element with a higher electronegativity. So the way we record that is we draw an arrow that points towards the element with a higher electronegativity. So that's chlorine, and we put a little plus at the other end. Because if those electrons are spending more time around chlorine, electrons are negative, and so chlorine ends up being partially negative. And that arrow is one way to record that. The other way is to use the Greek letter delta, that's lowercase delta, and then put a minus sign, and then the same delta sign over here with a plus. And those mean partially negative and partially positive. Let's get one more example into your notes, this time with something that has more than one bond. So I'm going to use water. Water is made up of 2 hydrogens with 1 oxygen, so I'm going to draw it in here. I've got my hydrogen and another one over there, and here's my oxygen. It's got 6 valence electrons, and then hydrogen has 1 each. So we can make a covalent bond between hydrogen and oxygen. We can make another one over here, and then oxygen can get both of those electrons shared sometimes, and so all of them end up with a full outer shell. Let me do this drawing over here a little bit more simply. Those circles get a little confusing after you get the idea, So there's my unshared electrons, and there's hydrogen over there. Now hydrogen's electronegativity is 2.1, and we know oxygen from over here was 3.5, and that hydrogen was 2.1. So if we subtract those, 3.5 minus 2.1, that works out to be 1.4, which is still between 0.3 and 1.7, so it's still polar covalent, which means those electrons are not shared equally. And so if I want to draw those arrows in, they would need to point at the oxygen, and the little positive end of the arrow is over there on hydrogens. Now I can also draw in those delta signs for partially positive, and then the oxygen is just partially negative. All right, for the last type of bond, ionic, that's what occurs when we have two elements with a difference of 1.7 or greater. All right, now we looked at magnesium oxide in a previous set of notes, and magnesium had 2 valence electrons, and then oxygen, of course, has 6. We've seen that already today. And back in that previous set of notes, we learned that one of those electrons and the other one can both go to the oxygen and complete its outer set. And that would get us Mg 2+, and then oxygen 2- with all of its valence electrons. But now let's look at those electronegativities. Magnesium has an electronegativity of 1.2, and then oxygen, that was 3.5. So if we subtract those, 3.5 minus 1.2, that works out to be 2.3, which is clearly greater than 1.7. That's what makes it an ionic bond. Covalent bonds would share their electrons, but ionic bonds have elements that are so different in their electronegativity that they will completely strip away an electron or give their electron away. Now be sure to pause the video and get your notes all caught up on this slide because I'm about to move on. All right, now looking back, we've learned about 2 types of bonds, ionic and covalent. But the third type of bond we need to learn about is metallic bonds. Remember that metals tend to lose electrons and form cations. Most of those we've been looking at would form a +1, a +2, or a +3 ion, and they lose those electrons in order to uncover a stable octet on an energy level that's closer to the nucleus. So over here in my drawing, I have 20 metal cations, they're pluses, and the electrons are all circulating around, but you notice they're kind of randomly drawn in. That's because the electrons aren't bound to any particular cation. They can flow around from one location to the next. Like this electron might start in one location and end up over here later. The electrons just aren't really attached to any particular cation. For this reason, the electrons are called delocalized, or another way to say it is they're a sea of electrons. And that's because they're free to float around all of the other ions. Now, if you got all of this into your notes, you're done with this video. I hope it's been helpful to you today, and as always, thanks for watching.